Hello, everyone, and welcome to the second session of the GAT of West Switzerland. Today, we have the pleasure of having Alex Bishop from the University of Geneva, who's going to be talking about the conjugacy depth function for Grigorchuk's group.
First of all, I'd like to thank the organizers for inviting me to speak. And thank you for the introduction. So in this talk, I will talk about conjugacy depth function for Grigorchuk group. So of course, I will define conjugacy depth and Grigorchuk group within this talk, so you don't have to worry about that too much. Okay, so let's begin. So of course, we'll start with some minor definitions. So first, just to clear up some notation. So within this talk, I will be talking about weighted generating sets for groups. If you don't know what a weighted generating set is, it's basically just if you have a finite generating set for a group, then to each generator, you associate a positive weight. And well, the weight of an element is just the minimum weighting of a word that you would need to represent that element, if that makes sense, just how it says in this definition of length. If you know the usual definition of length in a group, then that's just the one where you pick the length of each generator to be 1. And as usual, the two elements, let's say G and H, are conjugate if there exists some element of the group which conjugates one to the other. So G is conjugate to H if there exists an element X, such that X, H, X inverse equals G. And we say they're not conjugate otherwise. So, okay, this is all standard notation. So hopefully this is all okay. Okay, so I will have to tell you what conjugacy depth is. Conjugacy depth is only defined for groups that have a property called conjugacy separability. So a group is called conjugacy separable if for any pair of non-conjugate elements, G and H, there exists a finite quotient of your group, which also witnesses those elements not being conjugate. And if you have a conjugacy separable group, then you can measure how different two elements are in terms of the conjugacy by, well, what is the minimum size of a quotient that we would require to distinguish those two non-conjugate elements. And just for technical reasons, I'm just going to say that this function, conjugacy diff, that I'm defining here, it just returns 1 for if the elements G and H that you give it are conjugate. So basically, this function is just going to measure the minimum size of a quotient that you would require to correctly identify whether or not the two given elements are conjugate.
Could you give an example for the previous definition, from the last definition?
Sorry, of conjugacy separability or of
conjugacy? For both of them.
Oh, okay. So we'll see some examples of maybe some different conjugacy. Let's see. Okay, so some examples of some conjugacy separable groups. Well, we will see in this talk that Grigorchuk group is an example of such a group. Free groups are examples. Abelian groups, for obvious reasons, are examples. And virtually abelian groups, virtually nilpotent groups are all examples of conjugacy separable groups. And for this conjugacy difference, let's say maybe a stupid example might be take the group which is just Z, so just the infinite cyclic group. Then if you take two elements A and B in the group Z, then the size of the quotient that you would require would be 2 times the lowest common multiple of A and B. Because if you just consider the group Z modulo the lowest common multiple of these two elements, then you can distinguish them. Does that make sense? Okay, I guess silence means yes. Yeah, sorry. Yeah, sorry. Thanks. But later on in the slides, I'll give you some more examples of some bounds on conjugacy depth for certain classes of groups. Yeah, okay, that'll be in a few slides. Okay, let's move on a bit. Hopefully those examples were okay. Once we're able to define this function conjugacy difference, then I can define the conjugacy depth function of a group, which just basically says select any two elements in a ball of a given radius, then what is the maximum size of a quotient that we would need to distinguish those two elements? So in a way, this function, which I'm calling conj, C-O-N-J, in a way, this function measures how hard it is to compute the conjugacy in the group is, or how quickly it gets out of hand. And as we can see from this definition down the bottom of the slide at the moment, the conjugacy depth function at the moment depends on a weighting of the generating sets, because we're taking elements within some ball of a radius, and well, in order to take a ball in a group, you need a distance metric, and well, we have the distance metric with respect to some weighting of a generating set of a group. So okay, it's a bit of a problem, but we're going to fix it. Okay, so the first thing that I'll say is that when we talk about conjugacy depth functions of groups, we're only really interested in them up to an equivalence relation, which is, if you, maybe some people recognize this equivalence relation. It's exactly the same equivalence relation that you put on the growth of a group. We basically say that two conjugacy depth functions are equivalent if they only really differ by a constant multiple of their input and constant multiple of scaling, as you can see in this first definition. So I think that's okay. And so examples of things that are equivalent with respect to this equivalence relation, well, polynomials of the same degree are all equivalent. So n squared is the same as 2 times n squared. All exponentials are equivalent. So 2 to the n is the same as 3 to the n with respect to this equivalence relation. And exponentials grow faster than polynomials, that sort of thing. And so the reason why we define this equivalence relation is that conjugacy depth is well defined for a group, in that it doesn't matter which generating set you pick or which weighting you pick of that generating set, all of the conjugacy depth functions will be equivalent. So this makes things well defined. Now that I've defined that, I'm just going to have maybe one slide of just some background. So the question that we might be asking at this point is, well, what is known about conjugacy depth of groups? What can we say? Well, it turns out not a lot at the moment. It's actually a very new area of study. As we can see from these references that I have here. I mean, the earliest one I have on this slide is from 2017. For non-abelian free groups, so think of the free group of rank 2, the free group of rank 3, etc. We have an upper bound on the conjugacy depth function of the form n to the n squared, where n is the size of the ball, n is the input to the function. I know I was using r on previous slides, but yeah. So basically, if you take a ball of radius n, then that's an upper bound to the size of the quotients. So you may notice that I don't have a lower bound for non-abelian free groups or virtually abelian. Well, for non-abelian free groups, the lower bound, I think the only lower bound that you have, so the only thing that you can really put in this slot here, if you can see my cursor, is the cube root of n. So for non-abelian free groups, like the free group of rank 2, the conjugacy depth lies somewhere between the cube root of n and n to the n squared. So we've got a bit of a range there. So we don't really have tight asymptotics. As you can see, for virtually nilpotent, we know that it's bounded above and below by some polynomial of some degree, which depends on the group. And we have a series of results down the bottom of the slide, just for Reith products of two finitely generated abelian groups, where the only one that we know any asymptotics for exactly is z Reith z, where we know it's exactly exponential. So a lot of like really vague bounds are known, but not a whole lot in terms of tight things are known. It's a very new area of study. Now I'm going to move on to the next word that was in my title, which is the Grigorchuk group. So in order to define the Grigorchuk group, I'm going to first tell you about automorphisms of an infinite rooted binary tree. So just consider this picture going on forever downwards. So every vertex in this tree has 2 children. Then if you take any automorphism of such a tree, then that automorphism would preserve the root of the tree. I mean, because the root is the only node is the only vertex which has 2 adjacent things, so it can only be sent to itself by any automorphism. So, and we also know from then on that every level is preserved. And the important observation that we have now is down the bottom of the slide, where it's down the bottom of the slide, where if you take any automorphism of this infinite rooted binary tree, then you can kind of write that as just some automorphism of the left subtree and some automorphism of the right subtree, which I'm calling x0 and x1, and then also some permutation of the first level, so whether or not you swap the left and right subtree. So the Grigorchuk group is going to be we're going to see the Grigorchuk group is defined as a subgroup of this automorphism group. So I need to tell you what the generators are of the group. So the Grigorchuk group is, well, it's generated by these 4 elements here, which are called A, B, C, and D. What the generator A does is it swaps the left and right subtree of your infinite rooted binary tree. So it just swaps the left and right. And B, C, and D are just kind of defined like this, where you just go down the rightmost path in your tree. So if we saw here, just keep on going right, right, right. And with B, you flip the first left subtree, then you move right, and then you flip the next subtree to the left that you see, then you move right, do nothing to the next one, move right again, flip, and then right again, and then flip, and then it just repeats like that. Maybe this makes sense. I hope it does. So basically these pictures are just saying, okay, this is performing B to the root, and this is what we perform to each of these subtrees that I haven't drawn on the picture. So the thing to note here is that, well, A just performs no permutation to its subtrees and just permutes the first left and right subtrees. B performs A to the left and C to the right. C performs A to the left and D to the right. And D performs nothing to the left and B to the right subtree. So maybe you can see that from the pictures. So that's the Grigorchuk group. It's just the group generated by these automorphisms. Okay, so now that I've told you what the Grigorchuk group is, I need to talk about subgroups of it. In particular, I'm going to talk about what's called the stabilizer subgroups. Basically, the stabilizer subgroups are things that just don't do anything to the first m levels of the tree. So it just leaves those alone. It doesn't permute them at all. Leaves all the vertices on the first m levels of the tree alone. And then maybe perform some action to things below those, to the subtrees below that level. For example, this generator D, it doesn't perform anything to this first level. It leaves that alone. The next level doesn't perform anything. And the next level kind of starts performing some action. So D is in like the stabilizer of depth 2. Okay, so why am I interested in these stabilizer subgroups? Well, we have a bound on the size of the Grigorchuk group quotiented by these subgroups. So, for example, the size of the Grigorchuk group modulo the stabilizer subgroup of depth 2 is a group of size 8. And basically, as you might be able to guess, well, we're going to find bounds on the conjugacy depth function coming from quotients by these particular subgroups. Okay. So, oh yeah, and another reason why we're interested in stabilizer subgroups is that if you pick any finite index normal subgroup of the Grigorchuk sorry, that should be gamma, not G, any finite index normal subgroup of the Grigorchuk group, then that finite index normal subgroup is sandwiched between two stabilizer subgroups. So if we want to find a bound on the conjugacy depth, then we only really need to consider quotients by stabilizer subgroups. We don't need to consider anything else. So in this talk, I will be showing these bounds on the conjugacy depth of Grigorchuk group, so that it's bounded from below by an exponential e to the n, or 2 to the n, whatever you prefer, and bounded from above by e to the n to the 2.74. In fact, it's like something quite closer to that. So how do we show that? Well, the lower bound is actually kind of a bit boring. The lower bound on the conjugacy depth comes from a result by Burabi on something called residual finiteness depth, which I never defined in this talk. So basically, if you look at the definition of residual finiteness depth, it actually turns out to be a lower bound for conjugacy depth. And Burabi showed that it's e to the n, so we get for free a lower bound of e to the n. And for our upper bound on conjugacy depth, I'm going to have to tell you about how to solve the conjugacy in Grigorchuk's group. And there's an algorithm to solve the conjugacy problem in Grigorchuk's group. And from this algorithm, we end up getting a bound on the conjugacy depth. So as I said, I'll start by describing how to solve conjugacy problem in Grigorchuk group. So given two elements of Grigorchuk group, are they conjugate, yes or no? Well, in order to do this, maybe this is a bit complicated, but the first thing we do is we come up with this subgroup, which is called K of Grigorchuk's group. It's basically just, well, this finitely generated subgroup like this. And it's known that this subgroup is index 16 in the Grigorchuk group. So Grigorchuk group modulo K is size 16. And the reason why this particular subgroup of Grigorchuk's group is interesting at all is that it's has the property of being what's called a branch group, which I'll explain on the next slide. The way this algorithm works for computing conjugacy of Grigorchuk's group is we define this function called Q, which you just give two elements of Grigorchuk group, and it gives you back a finite subset of the Grigorchuk group modulo K, where from above we know that subset can be at most 16 in size, so it's always finite. And from the way that I define this subgroup, the way I define this function Q is that if this function returns an empty set, then we know that G and H cannot be conjugate. So basically this function Q, it almost gives you a witness to two elements not being conjugate. So if there's no witness to the elements being conjugate, then they're not conjugate. Okay? Just as some examples of just the generators of Grigorchuk group. So this is what you get. So these are all like subsets of G mod K. And I have this, and basically if you try to check if A and B are conjugate, then they're not, and you get an empty set back. So yeah, so this example just gives you a solution to the conjugacy problem in Grigorchuk's group just for elements of size 0 or 1 letter. I'll call back to this example later on. On the previous slide, I told you about some subgroup K, and I told you it was important for some reason. Well, the reason why this subgroup K that I had on the previous slide is interesting at all is it allows you to define this function, which I'm going to call lift. And this function lift is going to be able to tell you, suppose you're given two actions on the first left and right subtrees. Is it possible to find an element of Grigorchuk group which has those actions on those subtrees? So, given an action on these two subtrees, can you lift it to an action on the entire tree? All you really have to know is what the action on the left and right subtree are in the Grigorchuk group modulo the subgroup K. So it actually tells you quite a lot. The function lift allows you to lift elements from their action on left and right subtree to action on the whole tree. Yeah. Okay, great. Why am I telling you about this? Well, that function Q that I told you about earlier, if you work a bit hard and go through case by case, I won't tell you why this is true. You can actually compute this function Q that I had on a previous slide, as I have here. I have highlighted in orange, like the things that I want you to pay attention to. So if you want to compute Q of G and H, well, you only have to compute Q for how they act on their left and right subtrees. And we will see on later slides that the length of the things that are in orange are less than the length of G and H. So we will actually get like some simplification sort of thing. So, okay, if we want to compute Q, we just run through these cases. So, well, what I was really trying to say with that previous slide is, if you want to compute Q of G and H, then if G and H are both in the stabilizer of level 1, then we actually computing this Q of G and H ends up reducing to the problem of computing all of these 4 things on the left. If you can see my cursor, maybe you can't. And if G and H are not in the stabilizer of level 1, then computing Q of G and H reduces down to computing Q of G0, G1, H0, H1, and Q of G1, G0, H0, H1. So, okay. We can keep on performing these cases. And so I'll give you an example. So let's suppose we want to check if the elements AB, AB, and AC, AC in the Grigorchuk group are conjugate. Well, if we want to do that, then we have to compute these 4 sets. And if we want to compute these 4 sets, well, we have to compute these 8 sets. And now, if you're paying attention to a previous slide, you'll notice that each of these sets at the bottom here, Q, D, B, each of those are empty because of some examples that I had on a previous slide. So each of these Qs down the bottom are empty. And if you remember at all my recursive formula that I gave you from before, if we have no solutions for the leaves of this tree, then we can't lift them to anything up above. Oops. So we can't lift any of these solutions to any solutions higher in the tree. So basically there's no element that witnesses AB, AB, and AC, AC being conjugate, so they're not conjugate. Okay, so Q of AB, AB, AC, AC is empty. Okay, so now that I've told you about this, I'm going to talk about, well, what's different about the thing that I'm talking about in this presentation. So in the remainder of the slides, I'm going to kind of modify this algorithm for conjugacy in Grigorchuk group to work with finite quotients instead. So if you remember from before, this was how we defined our function Q, which we were using to check whether or not 2 elements are conjugate. And so what I'm going to do is I'm going to just subscript it with some number m. Function Qm is instead going to check if the 2 elements are conjugate in the Grigorchuk group modulo the stabilizer of level m. Okay, so instead of checking conjugacy in Grigorchuk's group, we're checking conjugacy in a finite quotient of Grigorchuk's group. So great. And one thing that I want to note, I'm not going to prove this at all. It's actually quite tedious to prove if you want to prove it. But if you only consider words of which contain 0 or 1 letters, then you only need to consider finite quotients by the level stabilizer of depth 4 before you start getting exactly what you get from the conjugacy in Grigorchuk's group. So, okay. What can I really say? Why did I tell you about this? Well, this was some tree that we saw in a previous slide. Notice that the leaves of this tree are all single letters. So from my previous slide, I can replace all of these with Q4. The leaves of this tree, I'm only checking conjugacy in a finite quotient of Grigorchuk's group. Okay, and this tree carries exactly the same information as the previous tree. So, okay, sure, why not? That doesn't tell you anything, whatever. Well, the important thing is that if you remember how I was recursively computing the functions Q on earlier slides, it was using these formulas. And what I'm going to do is I'm just going to take these recursive definitions and I'm just going to add m's everywhere. And this is also true. So what can I gain from this? Well, this is what we saw on the previous slide. Well, you can kind of take this tree and it carries exactly the same information as this. If we took these Q4s and they lift to Q5s, and again, we can lift that up again to Q6, if that makes sense. So it turns out that this function Q6, which is only considering conjugacy in the Grigorchuk group modulo the stabilizer subgroup of depth 6. So we've found non-conjugacy in that quotient. So basically what we have now is that the conjugacy difference of AB and AC is at most the size of that quotient. Okay, great, sure. And basically what I have from this, if starting from the top of this tree, if we then compute the depth of the tree, by which I mean like keep computing it until you reach a node which compares the conjugacy of two elements which contain 1 or 0 letters. If you have the depth of such a tree, then that gives you, that should be, instead of that 6 there in the lemma should be m plus 4. So ignore that. I'll fix that later. So, okay, if you have a bound on the depth of this tree, then you have a bound on the conjugacy difference of the elements that were used to construct the tree. Again, that 6 there should be m plus 4. I'm going to define the size of a node, a vertex in this tree to just be, well, to take the maximum length of the two elements, defining that node. Okay, great. What I'm going to show is that for each vertex of this tree, its children are only a fraction of the size of their parent. And so this is going to tell us that this tree is eventually going to end, and it's going to give us a bound on the depth of the tree. Okay, so how do I do this? Well, I use a weighting of Grigorchuk's group, which is from Laurent Bartholdi, which, I mean, it looks very mysterious when you look at it. But basically what it's telling us is that if you consider the length of what action the Grigorchuk group is performing in its left and right subtree and add those lengths up, then that total length is about 0.811 times the length of the element that you perform at the top of the tree. So this will make sense hopefully on the next slide. And if you work a little bit harder, you can find this other bound where basically what I've done here is just remove the plus sign from this lemma by Laurent Bartholdi. So if you only want to consider what the length of its action on the left subtree or its action on the right subtree are, you get a length reduction of 681. Okay, great. So why am I telling you about this? Well, from before, we had two cases for computing what our trees looked like. In each of these cases, we either have the size of our vertices either reduces by a factor of 0.69 or by a factor of 0.811. And if you work a bit harder, it's like, this isn't too hard to show, but maybe I won't. that this case 2, where we have 0.81 factor of length reduction, can only happen at most 3 consecutive times as you're looking from, as you're going down the tree. So every 4 times you must at least have, be reducing by a factor of 0.68. So basically this is telling us that with every 4 steps down the tree, the size of our vertex reduces by a factor of, well, this down here, this h is cubed times mu. So I haven't told you what it is, but yep. And now we have our final slide, hopefully. So let's bring everything that I've told you together. Basically what this says is, okay, so every 4 levels we're reducing in length by this eta cubed times mu. So if we perform this, if we go down the tree this depth here, then we only have to go down a constant number of extra depth before we end up with things, before we only have to compare things that are the single letters, before we start ending up with those comparing things that are B's and D's like I had in the previous slides. Okay, and as I told you before, we have this bound on finite quotients. So basically what I'm saying here is that if you take this value for m in the first lemma and substitute it into the m in the second lemma, then we get this bound on the size of the quotients that we require. Okay, and basically that's it.
Let's thank Alex for the great talk. Are there any questions for Alex?
Yeah.
Yeah.
Use my mic. Okay. Yours. Okay.
I'm sorry. What was the question?
Okay. Yeah. So the slide 21.
I'm sorry. Which slide?
21.
21. Yeah. Sorry. I should leave it on this slide. Yes.
But the lemma is true for every element G and H.
Mm-hmm.
Okay.
I'm sorry. Oh, yeah. The first lemma is for any element. So the first lemma is for the depth of this tree that we would obtain if we were trying to verify the conjugacy of the elements G and H. Yes. Yeah.
Okay. Okay.
Yes. Sorry, that wasn't clear enough. Yeah.
And how do we get the eta and mu in the formula, the log?
So the H and mu come from these cases here. So basically what I'm saying is that if we're in this case of computing this finite tree that I described earlier, then if we compare the length of the 2 elements we're comparing here to the length of the 2 elements that we're comparing here, then, well, their lengths kind of reduced by a factor of eta, if that makes sense. So this down here is meant to be, so this maximum here is meant to be a measure of the size of this node and the size of this node. And basically what I'm saying is that the size of this node reduces by a factor of 0.81, if that makes sense. And the important thing is that once you get down to, let's say, the nodes all being size, I don't know, 1 or something like that, then from some results that I didn't even mention in the slides, you only have to go a little bit deeper before the tree terminates, like a constant depth more before the tree terminates. And that's where that plus C comes from. And the reason why it's eta cubed times mu here is just because of this lemma down the bottom of this slide here. I don't, does that answer the question at all? Or?
Yeah, but now I have another question on the slide 20.
Yes.
On the left, the case 2, you have the length of on the left you have plus c, and on the right you have a plus the length of a.
Hmm.
How do you?
Or how do you account for that additive constant?
Yeah, yeah.
Oh, okay. So it turns out that if you kind of like recursively apply these formula, you are right, you will be picking up some additive constants each time. You are correct about that. But if you add up how much of these additive constants you build up each time, it ends up being a geometric progression. So if you perform this case 1 twice, then you'd be picking up a constant of c plus a constant of mu times c. Then maybe if you repeat this case again, then you'd be picking up a constant of mu squared times c. And so each of these, so yeah, you are picking up an additive constant each time, but it's bounded by a geometric progression, which is finite, which has a finite bound, if that makes sense. So there's like a bound on how much on the possible magnitude of additive constant that you can pick up. And maybe it's not so obvious, but you can kind of get rid of these additive constants in the asymptotics. Yeah. Does that make any sense, or is that okay?
Yeah, yeah.
Sorry. Yeah.
Any other question for Alex? Okay, then. If there are no more questions, we can thank Alex again and see you next week.
Thank you.